Okay. Yeah, Aziz bhai, thank you so much. All of you, thank you. Would love to hear more about your experiential wisdom and your thoughts. Aziz bhai, you want to take away? Regarding questions, do you want questions during the presentation or towards the end? Or how do you want to prefer it? How do you prefer it?
Let's do it towards the end.
Okay,
But
go.
if there is something that somebody wants to add, I mean, they are welcome to do so.
Yeah.
Okay. Yeah, right. So I just wanted to
actually, I suggest after one section or so, you say, okay, any questions before we move on to the next, right? Because I have gone through the presentation, so let's do it that way. Okay.
Okay. All right.
Yeah, and the rest of you, if you can mute yourself, that'll be fantastic. Thank you.
Okay. So what I wanted to share is, I started my journey in photovoltaics back in 1982, actually, when I joined Purdue. And that was because I think I had a professor who was working on a project for Jet Propulsion Lab, which was laser written solar cells. And that was my first entry into this. So I helped in this project, and I was really fascinated by this solar device. And I was very, very interested. But, my project at Purdue was different. That was just a short contribution at Purdue. And then I joined Ferro Corporation, where, photovoltaic was their main business. And that's how I got engaged in 1986, 87. And since then till now, I continue to work in this area. And so I wanted to share what I have witnessed throughout this journey with you. And I wanted to share from the commercial point of view, as well as from the technology perspective, both. So this is quite a fascinating field. So how do I go to the next slide here? Okay. So, what I wanted to do is split it into two parts. One is the technology part, and other one is the business part or commercial part. And there is so much information to share. So this was a talk I gave at IIT. And so the audience there was, students and faculty. So it was more technologically oriented, but I did put some slides about what happened in the commercial area. So I would be happy to address both to best of my knowledge. So let's talk about commercial aspects of solar energy adoption and evolution. So, today we are in year 2025, but this thing started way back, something like, my entry into it was 1980s, and which was interesting in itself, but it started much before that. So what you are seeing is there is a great acceptance of photovoltaic technology. And what I'm showing here is sources of energy for producing electric power. So this is important to note, that it is electric power generation. It doesn't still include the the transportation sector. So if you look at today, something about 28 terawatt is what is. Okay, I hope it is not my feedback. Can you hear, guys? Okay, good. So I think I have somebody else's feedback probably.
Mohanji, request you to go on mute, please.
Okay.
Thank you.
So I think what you see is this. Today, the energy need, electric power need, is somewhere around 24 to 28 terawatt, in that range. Exact number is still kind of fudged here. But installed solar capacity is somewhere around 5% of that energy need. And every year there is about 1 tera, I mean, right now it is about 600 gigawatts, so that is 0.6 terawatt of solar energy being, solar power being installed in the photovoltaic module form. So this plot here is pretty realistic prediction of what is going to happen. So if you look at it, for example, this, the solar PV is this area here. And you have, if you look at electric power production, there are two categories. One is called as a base power, another one is called as a peak power. So the base power is coal, oil, nuclear, hydro, where the capacities are sort of fixed. And the peak power is power that comes on when you need extra energy. And those are like gas powered plants, which can be fired, anytime. And we think that where solar plays a role is actually reducing the use of, the peak reliance on other sources of peak power, because solar, unless you start storing it, it is still, it has a drawback in terms of becoming a source of base power. So you would see here that, even after that limitation, now the storage, solar energy storage is also coming online. So that is going to change the picture. But this is pretty realistic picture of what you see. So, I mean, you can see that by year 2050, 25 years from now, the PV is going to be about 50% of the, it would be supplying 50% of the electric power needs. Okay, so that's the prediction. Okay, so now I think the question initially somebody asked, and that I'm going to answer. So, I started this thing, as I said, for the space project. And that time the cost of solar module was like $100 per watt, and nobody really cared because it was supposed to be this unique technology which gives you a source of power in remotest location, and the cost was not an issue. Then I think the major thrust came in 1980s when Jimmy Carter made a push after the oil embargo that we need to be major in solar power. And so this was the first wave, commercial interest wave. And in this wave, what happened was a lot of investment took place from the oil company as a defensive investment, not as an offensive investment. They were not interested in promoting solar power, but they wanted to show this green picture. So Arco Solar, Shell Solar, Mobil, all these guys invested in solar in hopes of doing this marketing campaign, but there was really not a commercial push. So the those days India was doing pretty well as well. In 1980s, BHEL, BEL, these guys were doing photovoltaic modules for military applications or remote area power applications. Now this commercial wave brought in what is called as a low-cost source of silicon wafer, which was a multi-crystal wafer. So there are two ways of two types of wafers. One is called a single crystal, which are grown by Chakralski or float zone technology. And then there are multi-crystal wafers where you take an ingot, which is kind of frozen, and you got multiple grains. It is not a single crystal. So to reduce the cost, the float zone technology or a CZ technology being very expensive, people got interested in multi-crystal. So in those era, I mean, the cost dropped, but it dropped to about $10 per watt. And that time, Department of Energy said that, okay, I mean, if this technology were to be viable as a grid parity technology, we need to be, down to $1 per watt. And so I participated in these programs, which are called Sunshot, etc. The whole idea here was to reduce the cost. So to reduce the cost from something like 1986 to year 2000, this was done primarily in the United States and in the Europe. And this was done through improving the efficiency. And how did they do that? I will touch upon that a little bit later. Reducing the amount of silicon being used by reduction in wafer thicknesses. So that continued till about 2000. And I think, again, in terms of Indian scenario, India was fairly neck to neck. I mean, didn't really get involved in basic silicon, but in a solar module efficiency wise, Tata BP Solar came on board, and they were pretty much state of the art. In 2000, the picture began to change very dramatically. And that's when the China got involved. And China made a heavy investment, strategic investment in solar, and they just addressed each and every area, whether it was the area related to increasing the efficiency, whether it was area related to creating the supply chain, whether it was area related to reducing the cost of raw materials. Practically in every area, they made a significant investment. Also, they scaled up the manufacturing process. So what DOE was asking was what China did actually. DOE said that if you want to achieve dollar per watt, you need to have higher efficiency cells. You need to have reduced the usage of silicon. You need to have reduced the cost of silicon. You need to have very large scale manufacturing. So all these attributes or objectives were achieved by Chinese company. And so today what you see is essentially, the cost has come down to, somebody quoted here, like 25 cents per watt at the module level. But the installation, after installation and so on, the US is still probably about $0.50. So we are past the grid parity, okay? So that has been achieved. So this has been the journey. So the first wave was basically dominated by oil companies. The second wave was dominated by technology improvements that US and Europeans achieved. And third wave was dominated by Chinese, where they made a significant investment in all areas. But the major technology really came from US and Europe. And US and Europe really strategically focused on the infrastructure for making cells and modules. So all the companies who were producing equipment like Applied Materials, these guys were supplying the materials to, supplying the equipment to Chinese. And now Chinese have also started making their own equipment. So going to now levelized costs, which is where we are focusing on. So, in 2010, the levelized cost is like it considers parameters such as how much energy you are producing over a lifetime of the solar module, how much you made an investment, and it takes into account the interest rates and all those factors. So there is an equation which you follow, and DOE has published that equation to calculate the levelized cost. So you use that equation to calculate this levelized cost. And in 2010, this levelized cost was 31.5 cents. And, right now, I know, Nataraj, I mean, in California, at the peak time, we are paying that much of price for the electricity. But today, the levelized cost of solar energy, photovoltaic energy, has come down to about 4 cents, which is way beyond grid parity. Okay. And in India, it is about rupees 2 per kilowatt hour, as per the data published by Indian companies, at rupees 69 per peak watt of system. And, so the Indians are paying probably, I don't know, 6 rupees per kilowatt hour. So for them also it is, solar is pretty good deal, okay? Now, this is another thing that, a lot of people ask questions like, don't you invest energy in producing the solar module? And yes, you do, but, the payback in years, in US is about 1 year. In India, because we have higher radiation as well as we have lower cost of installation, it is one of the fastest payback region. We can recover this in about half a year time. And so there is, you would see a lot of articles which deal with positives and negatives of solar. But I am in the camp where I believe that, all the negativity that is written about solar is just a propaganda. Solar is, photovoltaic technology really has great potential in solving the climate, warming problems. Okay. So now I think, you go from here and what is going on. So this is the data from 2000 to 2022. So you just follow the top chart, which is a cumulative chart of all the regions. And, in 2000, you were at 1 gigawatt of installed solar energy capacity, mostly photovoltaic. And today it is at 1 terawatt, so 1,000 times more in 25 years. So you can see that it had a very fast growth rate. And also the countries which are dominating, you would be surprised to know, 2 countries which are of great interest to the world, where a lot of population resides, China and India, are making significant progress in this area. So this is the
Can we take some questions?
so I think I can stop and take few questions. Yes.
Yes. So I had a couple of questions. I had already gone through a lecture. So this, as you said, 25 cents per watt is the panel price, in the world.
Right.
And even if you double tax here in US, it should be 50 cents, right? That's what you said. However, I'm saying it is a lot more, because for a 5 kilowatt system, we get quotes for about 12 to 15,000, right? A 5 kilowatt system should cost, at your logic, about $2,500, but it's not. So I'm just saying there's something going on, which is out of whack, right? So the solar adoption could be much faster in US.
Right. No, yeah. So the issue
Does
with
the cost
does
the cost include UPS as well as battery backup? Because whatever you have quoted is plain peak watt peak. It does not include UPS. And what the question was, that it includes UPS as well as battery backup.
No, it does not. I'm not the $15,000 does not use battery back, right? It is purely installation, right? So yes, you could argue US labor cost is high, etc. So even if the raw panels come in at 50 cents a watt, I'm saying there's so much, someone is making so much money, right? All they're doing is installing it on your roof, and they get a permit from your local utility like PG&E, right? But even that today, right? So that's one thing. Again, we cannot argue over here, but I'm just pointing out. And secondly, in that other chart, you said payback is 1 year or something. What do you mean by that? I mean,
energy payback. Energy payback is the amount of energy you put in to make the solar panel.
I see. And how much you get back. Got it. I got it. Okay. Not in terms of money. Okay.
Not in terms of money, but amount of energy. So I have a personal experience in the US. Okay. So I think my payback was 6 years. I installed the solar power about 12 years ago. And in 6 years, I was pretty much cost neutral. So I'm using free energy right now. So
no, same here. So same here. That time they were also giving back some rebates.
Right, exactly.
Yeah.
And I mean, I spent like on 6 kilowatt peak, I spent about 30,000, and I got some money back from US government in type of subsidy, but it is still more expensive than what you buy today. So I'm sure people's paybacks are pretty good. And also in California, I mean, if you start using peak power, you are spending upwards of 28 to 32 cents
Correct.
per kilowatt hour.
Correct.
So it is not pretty.
So that's what you take out. Yes. And the last question was, how come US is not in that chart, the total installed capacity? You're saying China, India is way more than US.
I saw
India
that.
was so high.
Yeah.
I think India was so high.
Yeah. No, I think US is there. I picked it up from the data published in by international organization, but for some reason I also noticed that the US line was missing from my chart. Maybe the color was not right. I would have to double check. Yeah.
Aziz, Abhay has a question. Abhay?
What is that?
Thanks.
Abhay,
Yeah,
Yeah,
thanks, Akhtar.
I'll ask after. Why? Hi, Aziz.
Hi, Pratmesh.
Yeah.
So go ahead.
So go ahead, Prathamesh. Sorry.
Yeah, Aziz, this is in India, what we have is if you are staying out of your flat or your bungalow, you can
Right.
sell it to the grid and you don't get any monetary advantage. It is in terms of credit. Does that
Right.
happen? We have two-way metering. The electric meters, yeah. So if you get
so
that
I have the
advantage,
same system. We have the same system in the US, which is called net metering. And
Okay.
but it is a pure theft because the government is buying solar power from me for 4 cents or 3 cents, something like that. And they are selling me, if I exceed the peak power, at 28 to 32 cents. Okay. So it's like, it is a rip-off, but I do get a credit. I get the negative, like meter goes backward. That is one credit. If I use less power, even that what I have consumed, then I get a credit at the rate of 3-4 cents. It is a very piddly rebate. So I get about $1,100 or $1,200 per year. Okay, I mean, that's not bad, but if I were to use more energy, they would charge me a lot more. That's what.
No, here it is the same. Whatever difference is there, you pay for that. That is all. And suppose if you are on vacation for 3 months, you have left your place, still it will continue to generate electricity, which will be fed into the grid.
Correct.
And you will get credit. So next few months, you will get credit. Of course, some portion of that, it is okay.
Yeah. I think same system. I think US is even the system is very similar. We actually get money back. But my point is that it's like government is also profiting from it because they are buying electricity from us at a lower rate and selling it at a higher rate.
Okay.
Government means the utility companies. It's not
distribution
company. Okay, let's move on.
Aziz, I had a quick question and a quick comment as well. So let me make the comment first. So Anil, to your point, when you say the modules are costing only whatever, right? So typically module cost today is only 25 to it's only 25 to 30% of the project cost. The rest of the cost is becoming land, inverters, switchgear, transformer, cables, SCADA. And then, like you rightly pointed out, US rate of labor is super high. So in India, typically the installation of men and material will be 10 to 15%. In US, I understand it's probably higher. So that'll probably explain why.
No, it does not. No, because I am only talking my home installation. There is no land acquisition, nothing.
Okay, got it.
Okay.
I will actually put a link over here. There is NREL in US, which is worked very closely with a lot of installers, and they've published a report on the costing. I'll paste it
Yeah.
just for academic reasons. But Aziz sir, thank you so much for holding this Zoom session. You all seem to know each other, so I'm like an outsider. But my question to you was, when you spoke about the evolution, one point which you very nicely said is somewhere on the second wave, China came in and kind of beat US to the race. And I remember Sun Power and First Solar were t- crazy technologies. What was the key reason, sir? What was it, the oil company lobbying just so that, because I've never found this answer, that how did China become like 70% of this market, and even today dominates?
So, I witnessed this interesting phenomena from 2000 that, we would have these sudden expansion of capacity. And then, the prices would crash. And they would say, this company is going to go bankrupt. I mean, in China, many companies like Suntech was very top company. There was Trina Solar, there was Solar Tech. All these companies went bankrupt, or they were taken over by some other company, Jinko Solar or something. So the government played a key role in backstopping solar. They basically did not allow solar to, because Nataraj made an interesting point, the rate of return on capital. The China, it doesn't, I mean, they say China doesn't care in the strategic area on the rate of return on the capital. And that might have been the important factor in continuing this, because today, there is a polysilicon, and which is a raw material, and I don't, yeah. So, the polysilicon prices, at one point there was a shortage, and the US company Wacker used to make this, and the prices went through the roof, $100 per kg, and it was like, it created havoc. And today there is so much capacity that they are talking about $6 a kg. So you can see why the solar module prices came down. Okay, and also, the premier company like BP or Tata, if they want to install 25 megawatt, they would be like, yeah, I had to get a permission, I had to do the calculation. And then Chinese are putting like 100 megawatt plants. And they are, I don't know what calculations they are doing, but it was a very quick decision and it was done. That was a major difference. I think the government played a role, and they considered it as a strategic of their strategic interest, and they made sure it didn't really die. Whereas US, I think they continue to invest, but have done it quite smartly. I think they made a lot of money in creating an infrastructure, also licensing technologies and so on, US as Europe. But now I think it is all China, and they are reaping the benefit, US, of course. They couldn't have done the modules at the prices that China is doing. And that has really helped the US as well in terms of reducing their reliance on the fossil fuel. So it has been good, but it is definitely China who played a key role.
Awesome. No, thanks for that, Aziz sir. And towards the end of it, if time permits, would love to know your thoughts on IRA post Trump coming into power on January 9th. Really keen on finding out.
All right. Okay, so let's talk about technology evolution. Okay, so Abhay mentioned NREL is a leading organization, and Fraunhofer ISA in Germany, and they every year publish this chart. And what this chart does is it lists all the technologies and their efficiencies. Okay, so as you can see, okay, what is going on here is I got to move this window somehow. Which is not possible. Okay, because I cannot see in the chart. Oops.
So it may show an option to pin or unpin that bar that you see.
Aziz, can you just highlight dye sensitized cell, and or you can share this graph or link with me.
I have a major problem. How do I start sharing the screen? I pause the screen share. How do I unpause it?
No. After the call, you can share it on WhatsApp or whatever is. We'll download it.
Yeah.
This slide, and with your permission, we'll refer to it.
Yeah, that's fine. But I'm just
No,
I lost the screen share.
Unpause it and then start the share again.
Where is the unpause button? That is the question. Share. Okay, I'm going to share. Let's see what happens. Okay, forget about it. Okay, I got it here. I was trying to, there is a window where I see everybody's faces, and it is creating distraction because I cannot see my presentation well. So I think Pratmesh, dye sensitized cell is a very minor technology. I'm going to, there is a lot to cover. So I'm going to focus on the major thing, which is crystalline silicon. Okay. So as you can see, the crystalline silicon is the dominant technology here. And I will, most of the data that I'm sharing is going to be on crystalline silicon. A little bit I will talk about other things at the end. Okay. But this chart shows the progression of efficiency, and I will come back to it. Okay. So basically, in today's world, crystalline silicon is the dominant technology. And there are two types of crystalline silicon technology, multi-crystal and single crystal. What we are seeing here is 600 gigawatt of production in 2023. And the light blue color is essentially monocrystalline silicon. The dark blue color is multi, and this, the greenish color is telluride, and that is just primarily for solar. So you can see in today's world, Chakralsky, CG stands for Chakralsky, monocrystalline silicon dominates the production. Okay. And initially, as I was mentioning to you, that in first wave, there was an introduction of multicrystalline silicon, but that kind of, in up to 2018 or so, that continued to have major role. After that, it continued to die down as the efficiency of monocrystalline silicon were significantly higher and made multicrystalline silicon less important, not for two reasons. One is the efficiency and the cost of the wafer and the thickness of the wafer. These three factors cause the monosilicon technology to be dominant technology. So, what I'm showing you here is three charts. You have, this is a multicrystalline silicon and that efficiency. This is monocrystalline silicon. And the third one is the heterojunction, which is also monocrystalline silicon. So, most of the production today is focused on a type of monocrystalline silicon technology as well as the heterojunction technology. The multi-silicon is very small. And today's maximum, yeah, go ahead. Okay. So let me get into the technical part, and I wanted to kind of give you analysis. I mean, how does this energy conversion process work, and how are we getting the efficiency and so on? Okay. So first of all, we have a solar radiation, which is being used to convert into electrical power. So for solar radiation, you have, depending upon your geography, you got irradiance time, is how long you can see the sun, and angle of irradiation, and the concentration. This is a minor thing, okay, because it is minor because commercially it is not feasible to use concentration. I mean, the levelized cost of energy from the concentrated solar cell today is still higher, though you get more power because you have to do a lot of stuff. And the third thing is reflection. I mean, as the radiation falls onto the module or the cell, you lose some energy in the reflection. So that is the, once the energy is captured, now it becomes, it goes to the PV device, photovoltaic device. And photovoltaic device is basically a PN junction. So there is about 52% of loss of this energy, which is purely related to, next slide I will show you that silicon has a band gap, which is 1.12. So if your photon, which is irradiating this cell, which has an energy which is lower than the band gap, then it is not going to be generating any carriers. And if your photon has an energy which is higher than the band gap, it is going to be just lost in thermal or transmission. Okay. So what the PN junction does is acts as a filter. So as soon as the carriers are generated, I mean, you can take a plane. So I was giving this talk at IIT, and the guy stood up and he said, I don't want to make a PN junction because I just have a silicon wafer and I'm going to irradiate it and I'm going to create a carrier. I said, great, Funda, you are asking me test question. So I'm giving you an answer that you don't have a filter, so you are not going to separate the carriers. Okay, you can generate as many carriers you want, but you don't have a filter, so you are not going to separate any of those. So the IITians still have this crooked mind. Okay, that never stops. So the junction acts as a carrier separation. Then I think once you have these carriers generated, then they have to be collected. So they have to migrate to the collector, and that's where the lifetime of the carrier, and if some silicon has a defect, if the silicon has defect, original defect in terms of wafer, either you create vacancies, you create inclusions, you have a stacking fault, all these defects have charges associated with it. So if carrier goes there and it is a charge defect, it is going to just neutralize it. Also, whenever you do the processing, you create defects. So the recombination becomes very critical. Okay. The lifetime is also dominated by the quality of silicon. Like we talked about float zone being highest quality, multi-crystal being lower quality, and Chakralski somewhere in between. So that plays a role as well, and there has been a tremendous progress. So you have to look at radiation. Now I got a junction, which is a filter. Now I created these carriers. I got to migrate them to the right side of the polarity, and there is a voltage. This voltage is pretty much dominated by, there is a band diagram. I'm not going to get into it, but it is pretty much dominated by the band gap and, the Fermi levels and so on. And, even though band gap is 1.12 eV, you can maximum voltage you can get out of crystalline silicon solar cell is 749 millivolts. Okay, so there is a loss of voltage, which is just practical loss. And then you have to collect these carriers. So there is a contact resistance. There is again recombination process during collection. And so as a result of all this, there is a calculation which was made, and it is called Shockley quasar limit. So practical limit for silicon is 29.2%. So that's all you can get after you do all this stuff. Okay. This is an interesting diagram. Gives you the points that I was making. Okay, you separate the carriers at the junction. So if you are able to collect it right at the junction, the probability of collection is pretty high. But you have to go further away, the probability declines. And that is the funda that both sides, which has been used to really improve the efficiency of the solar cell, is by improving the collection probability has been a major thrust. And all the factors which have been, the designs and everything which has been done are to improve the probability. And that is called as a, there are some dangling, the charges at the surface. They need to be passivated. So all the time, a better passivation schemes are arrived at, and latest technology is really focusing on the solar cell with the good surface passivation on the front and the back. Okay. So this is another chart, and this is also interesting because if, like I said, I mean, you can have quantum efficiency, means you can collect the 100% electron if you didn't have all these dangling bonds. So on the front side, you lose some collection, back side, you lose some collection, and in middle, you lose it because of, there are intrinsic defects. And then, of course, if you have a wavelength, after a certain wavelength, if the lambda is too high, then the energy is too low, so you are not going to excite any charge carriers. So that has been the other. This has been the fundamental for behind the solar cell efficiency. So on the front side, what has been done is, as I said, if the junction is very thin, you can improve the carrier collection. So the shallow emitter, that means higher resistivity junctions, passivation, the anti-reflective coating, so the light doesn't reflect. On the back side, I think, putting the surface field on the back side. So if the carriers reach the back side, they are reflected back. There is also back surface passivation and back surface reflection. So all these schemes are used, which translate to new design structure for the devices. Okay, so that brings me to the next topic, which is actually solar cell device architecture. Okay, this is a very interesting slide, and I am going to spend a little bit of time here. Okay, this slide shows actually, the blown out cross section of a solar cell. So you see silicon wafer. This slide is showing multi-crystalline, but you could have single crystalline wafer. Then you do to form a junction. Since if this is a p-type silicon, then you would do phosphorus diffusion to form NP junction. If it is an N-type of silicon, you would do boron diffusion to form PN junction. Okay. Then you put some sort of anti-reflective coating, and this anti-reflective coating is silicon nitride, which reduces the reflection. So if you take pure silicon wafer, the reflection is close to 30+%. So they have to use a lot of schemes. I mean, you have to put anti-reflective coating. So 30% of the energy could have been lost, which is really not lost because you have anti-reflective coating. You also have a texturization of the surface, which traps the light. And then you have a collection grid, which is, where you would correct the charge carrier. On the back side, you have, in this scheme, this is a simplistic scheme, you have this back surface field metallization, which is aluminum. So this is about 3 generation back technology thing, but it gives you some fundamental. Okay, so if you want to improve the efficiency, so from 1990 to 2010, this is the era when US was gradually improving the efficiency. So it was to reduce the the resistive losses through better contact, through passivation of the surfaces, back and the front, making emitters shallow, texturization to improve reduce the reflection. On the backside, forming the P plus charged layer so that the carriers are reflected back. So these are the techniques where the focus was, okay. Then came 2010 to 2013. So the focus was, these lines here are the areas where the light cannot penetrate through. So you lose about whatever this shading is. So you lose about 7% of shading. So now that has been reduced to 4.5. So, all the lines have become narrow and tall. So the fine line, the contacting of the shallow emitter continued. And then there was, just the back surface field was replaced by back surface passivation plus back surface field, okay. And that is called as a PERC technology. So that came into play. And in 2014, then actually there was a limit of PERC, and that limit, to cross the limit, then I think, introduction of thin insulator layers, which are passivation, very thin passivations on the front and the back, and the separation of generation and collection led to two different technologies, which are called as HJT and TOPCon. So this has been the history of solar research. So based on the last 3 slides I talked to you about, it is all about, you can generate the carrier, no problem. If you shine the light on the semiconductor, the junction is, you can make NP junction or PN junction. Then you have to make these carriers survive so that they are collected efficiently. And that's where efficiency gains are coming from. And, in addition to, so that's where the passivation technologies are playing a key role, and the back surface field. I'm going to talk little bit about this contact.
Aziz,
Yeah.
Abhay has a question.
Okay. Yeah.
So one question on the previous slide. This carrier is basically the electron which has started moving, right, out of that band gap. How does this back surface passivation work? I didn't understand that concept.
Okay, so the carrier N is the dominant carrier. Normally, for this original technology, people were using P type of wafer.
Correct.
And so if you do P type of wafer, then you form N type of diffusion on top to make NP junction. So on the N side, you would generate electron. On the P side, you have holes. So what they do is they put this P plus field, which is called as a back surface field, which acts as a reflector if the carriers are going to be lost on the back side. And so that acts as a barrier for carrier. They are pushed back into the towards the junction, and that's what is the purpose of back surface field. And if your carrier reach the backside, wherever metal comes in contact with semiconductor, it creates a lot of traps, and that is a destroyer of the carrier. So somehow you need to have a scheme where your carriers are protected from this, because the aluminum used to cover the entire backside. Okay, and you still have the bus bar which can carry the current, but if aluminum, if you reach the backside, then I think you would you would have a recombination. And so P plus back surface field reflects back the carriers, and it helps in terms of reducing the recombination. I have some data which I will show you.
Amazing.
Okay.
First time in my life I've understood how it works.
Okay.
Brilliant. So then, sir, when you buy a module which is mono PERC, only mono PERC will have that passivization layer. When I buy a normal polycrystalline module, it will not have a
No,
passivation.
so there are like, okay, so if you buy a multi-crystalline, I mean, there are, I will answer your question a
Later.
little
Okay.
later. Okay,
No
because
problem.
I have that I would answer it at that time. Okay, I'm going to skip this because it was meant for, you know, bunch of IIT students. Okay, how do you form the contact and so on. So it goes into the microstructure development of the contact. Maybe I will show you like one slide here. So the interesting thing is, you know, you have these grid lines. So this is the silver particle, which is part of the grid line. And this is a silicon wafer where the charges are residing. So how do you go from here to here is the question. And so what you see here are the precipitates of silver on the surface of silicon wafer. And then there is a glossy film in which also there are small precipitates. So they act as a conductive channel to transfer the electron from silicon to the bus bar or the fingers, as we say. Okay. And I'm going to skip this. So this shows you a little bit of flare. What you see here are the pictures where the top silver grid lines that you saw in earlier picture were etched out. And so bad cell, if you have a very bad cell, then the silver grid line and silicon wafer has a thick layer of glass, because the you know, to make the silver grid line stick to silicon wafer, we have to add the glass. So if you have such a situation, you get very low efficiency. Then, you know, good situation is where you have a thin layer of glass. You get, you know, and if you etch out the layer, now you don't see these big puddles of glass, but you see a bunch of these dots, white dots, which are actually silver dots, which form as a channels to carry the carriers from silicon wafer to the grid line. And then here you see very fine precipitates. So ideal, if you have a thick precipitate like that, it affects the diode quality because it penetrates inside the silicon. And as I was saying, like acts as a recombination. So it is not good. So we prefer something like this. Okay, so this was one of the things. The other thing is what is going on in the industry is, as I was telling you, these wherever these silver lines are, the light cannot penetrate those silver lines. So initially the technology had a very wide silver lines. Now the improvement has to make these silver lines narrower. Today it is even better than this. So I'm showing here 50 microns or so, and today we are down to 29 microns, 28 microns, etc. So the line widths are continuing to this. So now your question, the carrier selectivity at the backside of solar cell through electric field. So this is what goes on. So, you know, the backside of the solar cell, in the traditional solar cell, we used to form a back surface field by putting aluminum. So what you see here is a cross section. This is a aluminum, this is silicon wafer, and here is the back surface field. Okay, so this back surface field creates a barrier for the carriers. So this is P plus layer. So there is a bending of the diagram, and it is applicable for both. It is mono wafers as well as multi wafers. They both use this technique. So whether you buy mono wafer module, they would have a aluminum backside. If you buy multi, they would also have aluminum backside. Now, this was meant for students where I had to show them how does the microstructure develop. So I'm going to skip this. And this actually shows that indeed, this is how it is. because there is a simulation where you can calculate the thickness of the back surface field, and this is a thermodynamically calculated, and this is actual thickness, and they are off by about 200 degrees. And the reason for that is, thermodynamic is looking at the equilibrium, but when we are firing it, it is a non-equilibrium system. Okay. Okay, so again, Abhay, I don't know whether this would answer your question, but what back surface field does? So WBSF is the thickness of the back surface field, and S effective, it is the back surface recombination velocity. Okay, so if you don't have any back surface field, then the recombination velocity is 5,000 centimeter per second. So a lot of carriers are being lost, okay, before they are being collected and sent in the actual useful way in the solar cell. So if you have about 10 microns, which is normally 8 to 10 micron is the back surface field. So you have about 500 centimeter per second. So you are reducing 10 times. So that gives you improvement in efficiency. And the other factor is how strong is your back surface field. So that is given by doping concentration within that back surface field area. And stronger the back surface field, lower is the recombination velocity. So, it is combination of that. So, but there is a limitation of this technique, which lasted for quite many years. It lasted for 15 plus years. So the main issue here is, large area of metal is in contact with silicon, because a lot of aluminum is in contact with silicon. So it increases the possibility of recombination. So somehow we have to stop this if we want to have higher efficiency. And then there is absorption of radiation at the backside in the aluminum film. So then the new technique came about, and you may have heard called PERC cells. Okay, so in the PERC cells, it is a combination. They have a back surface field as well as a dielectric passivation. Okay, so in the dielectric, if you put the dielectric passivation, what happens is not only you passivate the defects, but you also have a reflection, high reflection from the backside. So you are able to reflect the carriers back into the solar towards the junction. So that helps in terms of improvement of efficiency. So the PERC cell is combination of dielectric as well as BSF, and a lot of work was done in the Europe, at the institutes like ISFH, ECN, Fraunhofer, ESA. These are the guys who did a lot of work. I was fortunate to collaborate with them from the material side of it. So how does this structure looks? Okay, so this is a cross section. So, this is P-type of wafer, this is N junction, this is silicon nitride, this is silver. On the back side, you got aluminum, and then you got bus bar. So this is standard conventional cell, BSF cell. In PERC, what you do is you put a passivation, which is aluminum oxide passivation, and then you form a localized BSF, but you don't have, what you do is you open this passivation by laser. So you hit the laser to create the holes in the passivation. So you need to have both BSF, back surface field, as well as back surface passivation. And if you did that, then, right now, I talked about the back surface recombination velocity with BSF alone being 100 centimeter per second, 500, but with the back surface passivation, it drops to 100 centimeter per second. So that drop in recombination velocity improves the open circuit voltage as well as the short circuit current. So both of them improve, and the efficiency of a solar cell is nothing but VOC into ISC multiplied by fill factor, which is a indication of how efficiently you're collecting. So that is more of the contacting the metallization to the cell. So since both of them are increasing, you get improvement in efficiency. So this shows a picture, ACM picture. So you can see here, this is backside of the cell. This is aluminum, this gray, and dark gray is where the passivation is open. So wherever the passivation is open, you see that it has reacted and it has formed this cup. And inside the cup, there is aluminum silicon alloy. And this ring here is the BSF. So you got BSF as well as you got passivation. So this is the technique on the PERC, and it is highly successful technology today, and it is being transitioned out to newer technology. But it also improved the efficiency. So if you go back to the NREL chart, which is hard to read, you would see there points what was the efficiency of the PERC cell. Okay. All right. So this is the same thing. I mean, I explained this in my earlier slide, so I'm not going to go into this. So now, this is another quantum efficiency measurement which confirms that the PERC cell has improved the internal quantum efficiency. Internal quantum efficiency reflects how much of radiation you received to how much it was converted into photons. And most of the improvement comes in the longer wavelength. And the longer wavelengths are reaching the backside. So most of the time, if you see efficiency improvement in the longer wavelengths, that are from the backside of the solar cell. Okay. And earlier I talked about BSRV decrease from 500 to 100. In this study, they are reporting decrease of 300 centimeters a second to 53. Okay, so same information. Now this is the data from ISFH, which basically shows that the efficiency of 20.1% was achieved. Now, if I roll back and I tell you that earlier in 1980s, the efficiency was 13%. So this is a huge improvement in efficiency in terms of without BSF, just anti-reflective coating, the efficiency of CZ cell was 13%. So all the back surface field improvement, back surface passivation improvement, created efficiency improvement of about more than 50% relative. So that is a big factor in terms of reducing the cost. Also, one more thing to note is this is not the latest number. The latest number is 22, 23 probably. Okay, so it is higher than this. Okay, so there is still limited in terms of PERC because you haven't done anything to the front side of the cell. You are focusing on the back side. So we need more improvement. And those improvements were delivered by two cell concepts, which are called as a TOPCon and HJT, heterojunction cell technology and TOPCon technology. Okay. And so what is this? What are these techniques? So in a TOPCon cell, you have N type of wafer, let's say, you form P plus junction, but right after junction, you introduce a very thin oxide layer, which is a passivation layer. Okay, so what you are doing is you are separating charge collection from the charge generation. So this metal, the carriers are actually tunneling through this 5 nanometer layer. And I think a lot of this is not a new technology. The semiconductor guys used it in MOSFET and all that, but it became common for solar cell recently. And also the companies who drove it were the Western companies, but now it has been taken over by Chinese. So they are pretty much dominant. So here, I think you have basically passivation on the front side as well as on the back side, which improves the solar cell efficiency. Here also you have the same thing in the HJT. You introduce a thin insulator layer. You separate the carrier charge generation from charge collection, and actually you form both sides. I mean, the back surface field, which is N plus layer, through deposition of amorphous silicon. You also hydrogenated amorphous silicon. You also form the same thing on the front side, PN junction, through the deposition, and not through the diffusion. It is through the deposition. So with the HJT and the TOPCon cells, now even higher efficiencies are possible. Now, these are successful technologies. Okay, these are dominant. Yeah.
So this HGT concept, thoda bouncer gaya. How do you have an N type and then you have an insulation and then you have again an N layer? What is
okay,
this part?
So as I was mentioning to you, these are called as this insulator layer is a thin layer, and this thin layer is for sort of a passivating the defects. So carriers.
So just to clarify, it will be like a junction so that the carriers can be channeled, right?
Carriers are channeled through this, yes.
Correct.
Carriers are channeled through this, yes.
So in an N-type junction, why would the carrier move? Sorry, I'm asking very layman questions.
No, okay. So these are not thick layers. These are only 5 nanometers. So that's the reason there would be a tunneling of the carrier through. So there is a physics behind it. So it is possible. Yeah. So I think there is a lot of physics which band diagram physics which plays into it. But this structure, you are able to move the carrier. I mean, the N layer is just like on the crystalline silicon. N layer, this is a N plus layer, so it is not a junction. It is N plus layer as a backside field layer. Okay, and this is a front side junction which is passivated with thin oxides. Okay, very thin. It is a 5 nanometer. So through that carrier can turn through. Okay.
Thank you.
And this is actually this is a amorphous doped hydrogenated silicon, which which combined with N type of wafer does form a junction. Okay, and you need an ITO here because you need to have transfer. I mean, this acts as an anti-reflective coating as well as lateral transfer of the carriers. Okay, for both of them. Okay, so these are highly successful now. Everything is okay, but industry did try a lot of other things, and these are important to understand. First of all, I mean, I talked about like wherever we have a front grid, you cannot have the light go through. So somehow we need to eliminate the front grid. So a lot of effort was done. This is called as an emitter back through. So they drilled the holes in the wafer, and both P and N junctions were on the back side of the cell. Okay, and this is still the same technique that SunPower uses. The only thing is they don't drill hole. They use very high quality silicon, and both P and N junction are on the back side. That is called as a back contact cell, solar cell. So here, I mean, since you don't have the shading losses, I mean, one were able to make devices which were 21.6 efficiency. The problem is the cost of making such devices. Okay, and that's why it didn't fly. I mean, it just died. Okay. The other idea that was talked about is make minimal grid on the front side, but not those bus bars. Okay, that thick bus bar was there. And then you carry that current through a plug to the backside of the wafer, and you collect current from the same side. On the backside of the wafer, you would have positive as well as negative terminal. And this was called as a metal wrap through. Again, this was not, I mean, it had a good efficiency, but did not succeed. Okay, and lastly, we have here a sun power concept, which is a back contact cell. And, unfortunately, this thing went something wrong here when I transferred the slide. But to give you an idea, the blue one is the N region, the red one is the P region. This is the N type of wafer, P junction on the top, and this is anti-reflective coating, and all the carriers are collected on the backside. And what it is showing you is the recombination on the front side, recombination within the silicon, recombination at the backside. So efficiency limit is 29%. The total losses are 1.4. So SunPower is able to achieve very high efficiency, 27.6. And so does HJT. Okay. So now what do we do? Going beyond the single junction. So obviously, I mean, one idea is, we are wasting part of the spectrum. We need to, utilize the whole spectrum. So these are called as a multi-junction or tandem cells. So we have, gas devices with various band gap, and you can achieve the efficiency, which is pretty high, like 52%, 41%, so on. This is being done in US actually quite well by a company called Spectra Power. And this is part of the huge aircraft, used to be, now it is taken over by something, but space grade cells, they are making using this technique. Okay. Then finally, I mean, there has been a lot of excitement on the new semiconductor, which are called as a perovskite. And because from the carrier generation point of view, they have a tunable band gap. So band gap is from 1.48 to 1.62, and you can change this band gap even further. So you can use it in multi-junction cell. The carrier lifetime is very good. So long diffusion lengths, long carrier lifetime. So migration wise, so it is helpful. Carrier collection is good because these materials have a higher dielectric constant than silicon. So it is, higher the dielectric constant, there is a formula, higher the dielectric constant, you can get a better carrier separation. The costs are low because you can make these perovskites using wet deposition technique, and you can form structures which are flexible, so you can wear them. So what is the issue here? The issue is stability. I mean, the efficiency degradation of perovskite is significant. Normal modules are lasting for now. I mean, there is a degradation curve, but you still get a significant power after 20 years. But these are something like 1.5 years. And there is a lead. These are lead based. So these are called, methyl ammonium lead chloride. And it is a AbO3 type of structure. And so there is a lot of effort being done to improve the stability and eliminate the lead. So where are we today? Okay. So remember the number 29.2. That's all we can do with silicon. So silicon monocrystalline cell in production, which is like 17,753, is running at 24.9. Okay. And you asked, a question about what happens to multi. Even the multi production is running about 20.4. Okay, so pretty close to what we can do. Okay, silicon is pretty much used up. CIGS is another technology. I don't think it went anywhere. And I don't think it would go anywhere. But you know, there is an investment made in California and CIGS, and you have efficiencies in 19.2. First Solar, of course, is dominant in CAD telluride, and they have reached 20% in thin film. And then new upcoming technologies. So in the lab, they have achieved efficiency of 25.2, which is magnificent. And then on a larger scale, they have reached efficiency of 19.2. So a lot of excitement around perovskite right now. Okay. And the next topic, you know, I think initially there was Pratmesh or somebody asked, like, you know, energy storage. And I think this is going to be interesting in coming years. I think this would be interesting for India as well, because, you know, we have, you know, remote areas and the grid, etc., are issue. So if you have a low cost energy storage, it would do the same thing what cell phones did to our regular wired phones. Okay, so over a period of time, like from 2010 to 2016, the cost came down by 75%. And we expect this curve. I mean, generally, energy industry has done better. And I think this curve would be beaten. And, so if you have $100 per kilowatt of storage cost, then I think, levelized cost of energy with storage would be, today it is somewhere around, 7 cents per kilowatt hour. And, by 2040, they are forecasting to be below 5. So by 2040, I mean, 7 cents is grid parity in some areas, and definitely by 2040, the stored energy would be at the grid parity. So, these are very renowned agencies, so I trust their data. They have been pretty good in generating trustworthy data. I wouldn't say reliable, but trustworthy data. So where are we today and what do we expect? So I think there is no doubt that PV has achieved the grid parity. The single junction cell has realized full potential of silicon. Any new energy deployment today is being dominated by photovoltaic. And the currently photovoltaic module capacity is about 1 terawatt per year. And deployment of this would, achieve that objectives that we talked about, like by within next 10 to 15 years, 50% of the energy would come from solar. Then I think, what do we expect? I think lower battery storage cost, which would make the rural electrification very easy. And also it would trigger the replacement of oil in transportation, because we are addressing still the electricity generation. There is another sector, which is transportation. Okay. In terms of tandem cells, they do deliver higher performance, but we need to reduce the cost. And then perovskite-based cells have a lot of potential in terms of flexible solar, variable solar, and so on. So thank you, guys. I'm open for any questions you may have.
Yeah. So after the life is about what, 15 years of these panels, right? 15 years?
25.
25. So how about recycling and waste management? Are we creating a problem for the next generation?
No, I think good question. So it is an industry which is being created right now to recycle the solar cell. Okay, and I think Europe is asking that we must recycle certain percentage of these modules. But yes, I think good question. But it is an upcoming area that complete what you call
I mean, there are no toxic or chemicals which create which have which make the recycling
environmental damage.
harder,
Yeah.
right?
So silicon is non-toxic.
Yeah.
Silver is non-toxic. There is a very fractional percentage of lead which would come from the soldering joints. So they had some lead, but those were old modules. So new modules that they are now lead-free solders. So that is not an issue. But you could get some lead from the old modules, but not from the new modules.
I have a question with regard to that.
Yes, Harish.
Hey, with great presentation. I have a question, a related question about cadmium telluride. I was on GE when we developed some of the technology that First Solar bought. Now, First Solar, you said, is dominant, but what about cadmium and recycling?
Right. So they claim that they would, take it from the birth to the grave.
Right.
So how do they do it? I don't really know, but they are taking the ownership of that cadmium. That's what they say.
What do you think? The efficiency of cadmium telluride is much lower than silicon.
Right.
So what is the market? What is the driver for cadmium telluride?
I think the cost of deposition is probably lower because but now I think one would have to really dig deeper because the polysilicon cost that time used to be $60 and it had jumped to 100 plus. Now it is $6. So how relevant is this cost play from thinner semiconductor? Because capital would be very thin and hence the lower cost. So I don't have a top of my head answer, but I'm sure I will find some publication. I will send it to you.
So there are two
Yeah.
quick inputs from me at Mahindra when we used to use First Solar modules. The two primary reasons we loved those modules is one, the size of the panels was much smaller. So the handling and breakage was lesser, although it was frameless, and the clips were easy to place. Second, the low light, diffused light performance of CDT was far better than polysilicon. So
Correct.
those were two reasons.
No, I think that is true. They are also claiming like temperature coefficient of efficiency is better than crystalline silicon.
Yes.
So those are the three factors they claim. The data is available. Because this has been going on for so many years that the solar plant data for crystalline silicon versus telluride cells is available. So you can see how the cells are performing, modules are performing over the years. So that data you should be able to dig up, but I haven't focused on that, so I didn't really get that. But I will see if I can find the data. I'm curious as well, what is the situation today? Because those, what Abhay mentioned are correct factors. That was one of the reasons for even amorphous silicon. They were saying, low light performance, better temperature coefficient of efficiency, and it's going to revolutionize. And AMAT really made a lot of investment, and everything was mothballed and nothing happened. So it is something that, I think that data should be looked at.
Is First Solar a good investment?
I don't know. I don't know. The stock seems to, now that Trump came into power, the stock must have dropped. But
Okay.
I'll tell you one thing. As you know, Aziz, I've been following this thing and I invested. I lost some money in this, Trina Solar and Jasso and all this.
Yeah.
Right. And then I also invested in silver because I saw, silver is being used, right? Silver is still not gone anywhere, right?
Right.
So, and then before that, wafer scale integration. Remember that company used to make wafers for the
MEMC.
right? Yeah, and they kind of went down. I mean, again, so just because you think there's going to be such a high volume, right? The actual investment thing can be anything. And I think First Solar, like you said, and there was another company called Solindra. They
Yeah,
pushed
yeah.
six, and
That
they
Yeah,
was
went
so
under,
in
right?
fact, that's a
yeah.
great question, Anil. I was going to ask Aziz, by the way, great presentation.
Uh,
Solyandra had, took
Six.
$100 million of venture money. They had some top scientists, and their whole claim to fame was cylindrical collector, right? Oh, yeah, Bola. I think Vidya was.
We can hear Anand talking in the background.
Yeah, yeah. I think he's muted. Yeah. So, Aziz, is that technology dead, or is there a chance for it to
Okay,
come back?
Solindra, and there was, I mean, I worked with this company because Obama funded it,
Correct.
Correct.
$740 million funding and so on. So not only that, there another claim was that they can make shingles also. Okay, so you
Roof,
can take
solar roof.
metal film and you can deposit SIG and you can make shingles. I mean, I'm really like, this is very tricky. I don't think it is going to go anywhere, to be honest, because I mean, silicon is so far ahead,
Yes.
and the costs are coming down. So all these nifty ideas are not going anywhere. I think it is interesting to see I wouldn't make an investment, but I would be really watching what happens to this perovskite. Does anybody solve the problem? Because Chinese are saying they have started installing perovskite factories. Okay, that is generally something that piques my interest, because when the silicon technology was left hanging, it was Chinese who started installing factories. So I would be really watching. Chinese did not do much investment in the SIGs and all that. So I would be watching actually the perovskite, what happens to these guys,
Uh,
yeah.
Aziz, this is related to dye-sensitized solar cell. Can we increase the bandwidth? Because for photovoltaic, you mentioned that blue to red, that is the limit. But for
Right.
dye-sensitized solar cell, we can have from ultraviolet to even radiation layer.
Yeah, so dye sensitized solar cell, I did not work on it, so I mean, it is hard for me to comment. I think what I hear about the perovskite though is the same what you are talking about, which is they have a wide range of band gaps. Okay.
Mm.
And so it is possible to make tandem structures and cover multiple sectors of wavelengths. Silicon covers pretty broad spectra, but you can cover other spectra, which
Yes,
originally only gas and gallium, indium technologies were able to do. So now this is a low cost way. But I really did not work on dye sensitized that much. I mean, it was something that was there, but our main interest was crystalline silicon. So I
I
continued.
think the lab models are successful for DS dye sensitized, but commercially it is nowhere close to success.
Right. I mean, I
Which is
understand the efficiencies are very low. So you should go to that NREL chart and see what the efficiencies of dye sensitized are. Okay, and so dye sensitized guys were like this military power. So, the military guys have to carry communication equipment. And if their, gear that they are wearing can generate the electricity to power that communication equipment, it makes it a lot easier. But the same market now, I mean, not only that, but these perovskite guys are talking regular market, because their efficiencies are in 25%, which is phenomenal. Dye sensitized was very small, so I can't flick back the slide because I'm worried that I would mess up. But you should look at the NREL slide which shows where is every technology in terms of efficiency.
You can share that on WhatsApp group. We only
No,
that
it is
slide.
there in this presentation. Nat has sent the presentation.
Yeah, I sent the
Okay.
presentation.
Yeah, it should be there. I talked through that slide first, so you would be able to see it. Yeah.
Aziz, I have a question.
Uh-huh.
This was more like a use case. So if we are looking at an ashram, for example, about 2 acres land, and we visited Muniseva ashram, and I have posted a link in the chat session here. So they are using a solar concentrator, a parabolic concentrator.
Okay.
So what are the options that we have? Just the panel layout on the terrace somehow, or use a
A
concentrator?
lot of
or
options.
what?
Lot of options.
So
Actually,
how do we go about this then? What's the best way to analyze and figure out how to reach a decision?
okay. So I think, I saw the levelized cost of various technology. I mean, concentrated cells do have high efficiency, but with all the mirrors and everything, the cost is pretty high. I mean, I think the number was something like 8 or 10 cents, okay, for a concentrated cell, whereas this one is down to 4 cents, okay. So higher efficiency doesn't mean that it is economical, but if you have a space limitation, then you are bound to use high efficiency. The other thing is, like, there are other technologies that I didn't talk about, bifacial cell. So you have a cell where both sides of you have module where both sides of the modules are able to generate the power, front side, and there is a rack which actually tracks the sun, and it flips the module and all that. So there are people who have done bifacial cell installation. So it is really cost and performance. I mean, the calculations can be done because there is a lot of support, calculation supports coming from Western institutes, like 2 or 3 institutes that I really like. One is like NREL, of course, gives you a lot of information how to do a lot of things. The second one is ESA, Fraunhofer ESA in Germany. They also publish a lot of information. The third one is okay, UNSW in Australia. Okay. So these guys, I mean, UNSW has slowed down. They used to be pretty good. But ESA continues to dominate. ISFH in Germany continues to dominate. And REL, as always, has been a pillar of this. So they provide a lot of information. So if I would make a couple of notes. One is that I need to dig up the information for Haris, and I will also dig up the information for you on the concentrated cells and calculations that they are doing.
And the other question was about the impact on the environment, particularly on the wildlife ecosystem. I vaguely remember some news article that in Nevada, there was a huge coverage of solar panels and a lot of birds dying there for some reason. And I don't remember
No, it
why.
wasn't the birds. That's for the windmill.
Windmill.
This
No,
was like
windmill was a different thing. Windmill is it's mentioned in the evolution book also that birds they cannot see straight. They can only see downwards, and they collide into the windmill. So that was a different thing. But this was about something in Nevada.
Yeah,
with,
it was some not crab, something like that. And Arnold Schwarzenegger had jokes saying, "Hey, do you want to save this, some creature, or do you want electricity?" I remember that. Yes.
Mm-hmm.
But I think they're the least, environmentally this thing. But anyway.
Yeah.
Yeah.
So
No, I
if
think
anything is
there
more,
are.
then.
No, Jayesh, I mean, interesting idea for solar is there are farms in California, where they grow cattle. And if you are driving on Highway 5, which Nataraj does it very often, so you get these farms where are solar modules which are providing shade to the cattle. And
Yeah, there was a thought here also that on the canals where they do the irrigation,
right.
if you cover them with solar panels, then you save the evaporation also and also get the energy from the solar panels.
Absolutely. And you know, parkings in India, I mean, there are less. You wouldn't have space, but parking in, I mean, on the West Coast, all these parks, you know, Apple Park and whichever all these companies, their parks are covered with the solar modules.
Yeah, all the
Right.
schools are
Yeah.
school parking lot. High
Yeah,
school.
all the parking. Yeah.
But see,
For the
my
canals,
feeling
for
is
the canals, even the efficiency goes up because it cools the panel from below. So that
Okay.
efficiency also goes up by 10 to 11%. That is what I read somewhere.
No, the efficiency, I'm not sure 10 to 11%, Pratmesh, but if you, there is a curve, temperature curve for efficiency. There is not like a very steep drop, but there is a coefficient of efficiency curve. And if you have a lower temperature, this is one of the issues that was brought up on the thin film side. In desert area, the temperature rises to 50 degrees C. So there is a significant impact on the efficiency. And so they said, okay, amorphous silicon has this lower temperature coefficient of efficiency. And so they are better. So you need to then monitor the performance over a lifetime to see how much energy is being produced by both modules and what was the cost, and feed it into levelized cost equation. And it's silicon still comes ahead, no problem.
Of course, we have a totally different problem that nobody has been able to solve yet. There is a menace of monkeys, and they have they have destroyed the solar water heater pipes. They have destroyed the solar panels on the terrace, and
Wow.
we don't know how to reduce that problem, how to get rid of that problem.
so. This is like the IIT. You remember the monkeys invaded in one shift here. People lost their shirts.
Literally.
Hey, Aziz, hi.
I
This,
will.
hi. Hey, so this was like fantastic presentation. I mean, it it shows that. I mean, in IIT, we used to like revere you for being the smartest guy, and now it
Oh,
just
no.
proves again. But
This guy
anyway,
is absolutely crazy. He
no,
consider me smartest guy.
no.
He is the
So,
smartest guy. He didn't study, so I got the silver medal. He was way smarter than me, but he was like doing all this mood indigo stuff and whatnot, and you know. So he was rarely studying. So he gave me a break. So
no, anyway. So, I have a question on transportation. So, I think you mentioned that, but I didn't completely grasp. So, the cost of transportation, using solar panels to generate the electricity and then using the lithium ion cells to store it in the car and to drive it versus using the solar panels to generate hydrogen, green hydrogen, and using the hydrogen to drive the cars. Do you know any statistics that shows which one is better in terms of just cost, not in terms of environmental impact?
Oh, yeah, I don't know top of my head, but there is that that's a totally. I mean, since I'm not part of that area, I just came across article and I forgot. But there were a lot of these factors, curb to the car and I mean how the energy flow occurred and what was the cost of each step. So I mean, but there is some analysis which was done. I don't have.
So Toyota bet big on this fuel cell Mirai, right? But America has lacked in hydrogen generation. They say, of course, environmentally that's the easiest because you can actually, water vapor comes out as a byproduct of the car, right? The fuel cell based battery. But yeah, I mean, the air in US is not doing anything about hydrogen generation, right? So
No, there is a blue hydrogen, there is a
No, plug
green
power.
hydrogen.
No,
So,
Plug Power and all these companies, but
yeah.
they're saying China is ahead there as well, right? And they say
Ah.
in the long term, like for the big buses and trucks, because the batteries become very heavy and it's not very
Right.
economical, right? Now the like you have a big truck, semi truck, they are saying hydrogen is a better technology. So there are a lot of these things there.
No,
Right?
no, Anil, my cousin heads fuel cell research for ISRO,
Yeah,
and he was here over Thanksgiving. I was talking to him, and he said that the cost of the platinum is so high, right?
I see.
The economics just will not compute unless it's a very specialized application like a satellite or a rocket or one of those things, you know. So
No, but see, you are probably right. Again, I don't know. I was just going by, I go by what commercially, right? Toyota, company like Toyota didn't bet on electric. They were for the longest time saying hydrogen fuel cell is it, right? So they must have done some analysis and thinking, okay, as long as we get hydrogen, right? In our area, only in Saratoga by that, Sunnyvale, Saratoga Road, there was that station, and often it's out of hydrogen. So it was just totally failed. But yeah, okay.
Yeah.
I feel the US should at least let this now that Chinese have driven the cost down, we can save a lot of our energy costs if US just lets in. Okay, as it is, there's no solar panel manufacturers left pretty much of any significance. So let the Chinese panels in, let the batteries in. Today, if they let those in, I think Tesla will go out of business. I believe because the battery prices have come down like anything, right? And then like the BYD can sell a car half the price with same features as easy if they. So US could benefit. I don't know, what Trump's going to do, but. And like I said, my own house, stupid people, PGN is another, right? So now they reduce that net metering to net metering something else, where they say we will only reimburse you at the cost of what we pay to other providers, right? So PGN is procuring electricity from all over. They say, hey, just because I'm procuring from you, I'm not going to give you the full price I charge. I'm going to give you the cost I pay.
Yeah. Oh, they are doing that all along. I mean, SDG in the area. As I said, 3 cents, 4 cents, I mean, nothing.
Yeah.
Yeah.
Okay, guys, I need to drop. Very nice. Aziz, I
Thank
think
you.
I
Great
confused
presentation.
Aziz with.
I know it's must be very, very late your time. Thank you so much.
Okay.
Yeah, Anil, go ahead.
No, I said, you are based in India right now, or you are in US?
No, I'm based in US, but I'm visiting India right now.
Oh, Isliya. Okay.
Aziz's kids live in the Bay Area, boss.
Yes.
No, also I confuse Aziz with that other person, Safe. So, anyway. I'm from H7. I guess I didn't run into either of you in IIT days. So. Okay, guys. Hey, Nat, thanks. And of course, Aziz, big thanks, and everyone. Nice
Hey, guys.
Thank you so much.
Thank you.
Okay,
Have
bye.
a wonderful holiday season and have a great, great New Year. So take care.
Okay.
Thank you.
Thank
Thanks.
Thank you.
Thanks a lot.
Thanks,
Bye.
Nat, for organizing.
Oh, you must.
Bye.
Thanks.